Namaste everyone and welcome back to coinslive. In this video, we will we are going to solve LeetCode problem number 34. Find first and last position of elements in sorted array. This is a medium level binary search problem and it teaches us an important idea. How do we modify binary search when finding the target is not enough? Let us first understand the problem. We are given an integer array called nums. The array is sorted in non-decreasing order, which means the elements are arranged from smaller to larger, and duplicate values are allowed. We are also given a target value. Our task is to find the starting and ending positions of that target in the array. If the target does not exist, we must return -1, -1. There is one important condition. Our algorithm must have runtime complexity of O log n. Let us understand this using the first example. We have nums equals 5, 7, 7, 8, 8, 10, and target equals 8. The first occurrence of 8 is at index 3. The last occurrence of 8 is at index 4. Therefore, the answer is 3, 4. Now consider the same array, but this time the target is 6. So target equals 6 now. Since 6 is not present in the array, the answer will be -1, -1. The third example contains an empty array. So this time our nums equals an empty array. Since there is no elements, the target cannot be found. And once again the answer is -1, -1. Now before writing the solution, let us think about the possible approaches. A simple approach would be to scan the entire array from left to right. When we find the target for the first time, we save that index as the starting position. Then we continue scanning until the target ends and save the final index as the ending position. This approach would work. However, in the worst case, we may have to examine every element of the array. That gives us a time complexity of O of n. But the problem specifically asks us to solve it in O log n time. Since the array is sorted and the required time complexity is O log n, this is a strong indication that we need to use binary search. However, there is a small challenge. A normal binary search finds an occurrence of the target. It does not necessarily find the first occurrence or the last occurrence. For example, suppose the array is the same array 5, 7, 7, 8, 8, 10. If we perform a normal binary search for 8, it may return index 3 or it may return index 4, depending on how the middle index is calculated. But our problem requires both positions. So we need to modify binary search. The main idea is to perform binary search twice. The first binary search will find the first occurrence of the target. The second binary search will find the last occurrence of the target. Let us understand how we begin the first occurrence. So idea is to perform two binary searches to get first and last occurrences. How we get the first occurrence? We begin with two pointers, left equal to 0 and right equal to last index. Let's say the size of the array is n. So right equals n minus 1. We calculate the middle index. If the middle index is smaller than the target, then the target must be on the right side. So we update left equal to mid plus 1. So mid equals left plus right minus left by 2. So this approach helps us overcome the overflow error that the integer size has exceeded. Integer in every programming language have some fixed size. After that, fixed limits. After that limit, if we try to keep that value, then it will give us an error. So to avoid that, we don't do left plus right, but instead we subtract before division. So if the mid is smaller than target, if my nums mid is smaller than target, then we update left equal to mid plus 1. We update left equal to mid plus 1 because we understand that our now search space will be, for example, if our search space was left to right, and now our mid is somewhere here, left, let's say this is mid, then right. Now we know that uh, nums mid is less than target. The number at this value is less than the target. So it is definite that because it is in ascending order. So all of these values will be less than target, left to mid, including mid. All of this will be less than target. So our new search space will be from here to here. That's why we update left equal to mid plus 1. And in the other case, we will update right else. The second condition is that nums mid is greater than equal to target. So we update right equal to mid minus 1. Or we can say mid also, because we are checking that we want the first occurrence. So in the first case, when nums mid was less than target, we know for sure that the our target cannot lie in this range. So we remove that. How to remove that? We simply update left equal to mid plus 1. Then the new search space will become like this. This will be left and this will be right. So let's say it is L and it is R, right. And in the second case, we update the search space in this way. It is left and then it becomes R, right. Now comes the most important question. Suppose the middle element is equal to the target. In a normal binary search, we would immediately return the middle index. But here we do not return. We first save this index as a possible answer. Then, because we want the first occurrence, we continue searching towards the left side. So we update right equals mid minus 1. This is the key modification. Even after finding the target, we continue searching to check whether the same target appears at an earlier index. Now let us understand how we find the last occurrence. The initial binary search process remains the same. If the middle element is smaller than the target, we move left to mid plus 1. So again, left equal to 0, right equals n minus 1, and mid equals left plus right minus left by 2. And if nums mid is less than target, we move left equals mid plus 1. And else, if it is less than equal to target, we move right equals mid minus 1. It is not for less than equal to, but nums mid is greater than target. But when the middle element is equal to the target, we save the index and continue searching towards the right side. So we update left equals mid plus 1. This allows us to check whether the target appears at a later index. So basically we can write it simply if nums mid is less than equal to target, then we do left equal to mid plus 1. Else we do right equals mid minus 1. Therefore, the difference between finding the first and last positions is very small. For the first occurrence, after finding the target, move towards the left. For the last occurrence, after finding the target, move towards the right. Let us now look at the pseudocode. So let me write the pseudocode. We create a helper function that accepts the array, target, and a boolean value. So inside the function, we initialize left equal to 0 and right equals length of nums minus 1 and answer equals minus 1. The value minus 1 means that we have not found the target yet. While left is less than or equal to right, we calculate the middle index. If nums mid is smaller than the target, we move left to mid minus 1. Sorry, we move left to mid plus 1. If nums mid is greater than the target, we move right to mid minus 1. Otherwise, we have found the target. We say answer equal to mid. If we are searching for the first occurrence, we move right to mid minus 1. Else, we move left to mid plus 1. So if we are searching for the first occurrence, we move right to mid minus 1. Otherwise, we move left to mid plus 1. Once the loop ends, we return the answer. And we call this helper function twice. So let me define this function. This is the function find boundary. And we call this helper function twice. The first call finds the first position. The second call finds the last position. Finally, we return both positions inside an array. Now let us write the Python code. We begin with the solution class. Inside the class, we define the search range method. This method receives nums and target. Inside the method, we create a helper function called find boundary. The helper function receives one argument called find first. This boolean value will tell us which boundary we are searching for. We initialize left equal to 0, right equal to len of nums minus 1, and answer equals minus 1. Now we run a while loop while left is less than or equal to right. Inside the loop, we calculate mid equals left plus open bracket right minus left close bracket integer divide by 2. This is safe way of calculating the middle index. Now we compare nums mid with the target. If nums mid is smaller than the target, we write left equal to mid plus 1. If nums mid is greater than the target, we write right equal to mid minus 1. Otherwise, the middle element is equal to the target. We say answer equal to mid. Now we check the value of find first. If find first is true, we want to search for an earlier occurrence. So we write right equal to mid minus 1. Otherwise, we want to search for a later occurrence. So we write left equal to mid plus 1. After the loop finishes, we return answer. Outside the helper function, we find the first position by calling find boundary of true. Then we find the last position by calling find boundary of false. Finally, we return find first position, comma last position. Now, let us understand it deeply by doing this dry run. Anyways, this is very simple. Let me show you the visualization once again. So this is my array left and with left and right. And let's say I found the mid position. Let's write its mid by the value m. Now in the first case, my number at mid is less than the target. That is the first case. Nums mid is less than target. So in that case, what I will do, because it is less than target, then I definitely know that all of these values will also be less than target. So I will simply remove this from my search space. I will search from search here. Now I want to So this will be my new search space. I will write this as left, but there is one question. So this is for first case. Let me write it as when nums made is less than target. Now for the second case, I choose this and this I choose when nums made is greater than target. But when it is equal to target, then what I do is, because I want to choose the first occurrence. When nums made is greater than target, then I definitely know that it does not lie in this range, not even this, because it is greater than target. So all these numbers will also be greater than target. So my target does not lie in this highlighted range. So I reduce my search space to this portion. But when it is equal to target, now if I want to find the first occurrence, then I need to include this value and go towards the left, because I want the first occurrence, not the last. But if I want to get the last occurrence, then I will choose this one. So when it is equal to target, less than or equal to target, so let's say my range will become like this. My search space will become like this. When nums made is equal to target. When nums made is equal to target and get first occurrence. Because I know at this position my target is there, but it is possible that there can lie some more targets on the left side also. So that's why I search on the left side. So now I will not. I can remove this from the because this I have already this mid element I have already found. So I can remove this from my search space. And in the second case, my search space will become this. This is when nums mid is equal to target, and I want to find the last. Because it is possible that although this is my target value, this mid is my target value, but there can lie some more targets in the right side. So that's why I search from left from in this search space. Now let us try run one example. We have this nums and target equals to 8. First, let us find the starting position. So initial left equal to 0 and right equal to 5. We calculate the middle index. Mid equals 2. The value at index 2 is 7. Nums mid is equal to 7. Since 7 is less than the target, we move towards right. nums mid is less than target. So we do left equal to 3, mid plus 1. Now left equal to 3 and right equal to 5. The middle index becomes 4. Nums mid this time becomes equal to 8. We have found the target. So we save answer equal to 4. However, we are searching for the first occurrence. Therefore, we continue searching towards the left. So we update right equal to 3. So right equals mid minus 1. Now left equal to 3 and right equal to 3. Mid will become equal to 3. Value at 3 is also equal to 8. So we save the answer equal to 3 and again we continue towards searching the left. Searching towards the left. So right equal to 2 and right is now greater than is less than left. So loop ends and we get our first position. First position equals to 2. Now let us find the ending position. We again begin with left equal to 0 and right equal to 5. The middle index is 2 and value at mid equals to 2 and nums mid equal to 7. The value at since 7 is smaller than 8, we update the left equal to 3. Now the middle index becomes 4. Mid equals to 4 now. The value at mid is equal to 8. Now this is equal, so we save the answer equal to 4. This time we are searching for the last occurrence. So we continue searching towards the right. We update left equal to 5. Left equal to 5. Now both left and right are 5. So middle index equal to 5 and nums mid equal to 10. Since 10 is greater than 8, we update right equal to 4. And now left is less than right. So loop ends. And our saved value was 4. So answer we return is 3, 4. Now let us understand why we need the answer variable. Whenever we find a target, that index is a valid answer. However, it might not be the final boundary. For example, while searching for the first occurrence, we may first find the target at index 4. But the same target may also exist at index 3. So we save index 4 as a possible answer and continue searching. If we find an earlier occurrence, we update the answer. Similarly, while finding the last occurrence, we save the current match and continue searching towards the right. If we never find the target, the value of answer remains -1. That is why the solution automatically returns -1, -1 when the target is absent. Let us also check some edge cases. So the first edge case is an empty array. So if my nums equal to an empty array, then left equal to 0, right equal to -1 and loop ends. So I get answer first index, first position equal to -1 and last position equal to -1. Suppose let's take another example of edge case. Nums equal to 8 and target equals 8. So my left will be equal to 0 and right will also be equal to 0. So mid will become 0. Nums mid equal to target. So what I will do for the first position, I will change my left to uh, mid -1. This was the condition, right? If I find first, so right equal to mid -1, which is right equal to mid -1. So right becomes equal to -1. Now right is less than left, so loop ends and first position becomes equal to 0. Now for the last position, left equal to 0, right equal to 0, mid equal to 0, nums mid equal to target. So this time my left will become equal to, as we can see, left will become equal to mid +1. So it will become left equal to 1. Now right is less than left. So loop ends and last position equal to 0. So we return answer equal to 0, 0. So things are valid for all the edge cases also. Now let us try to run the code and see if it passes basic tests or not. Okay, let us now also submit it. So all the test cases have passed. Now let us discuss its time and space complexity. We perform two binary searches. Each binary search takes O log n time. Therefore, total time complexity is O log n plus log n. So time is O log n plus O log n. And we know that if we do sum, it remains the same. O operator gives us sum same. So it is O log n. 2 O log n is equal to O log n. The space complexity is O of 1 because we only use a few variables such as left, right, mid and answer. We do not get any additional data structure based on the size of the input. So space is O1. Now let us discuss common mistakes. So the first common mistake is returning immediately after finding the target. If you return as soon as nums mid equals the target, you may return any occurrence, not necessarily the first or last one. The second mistake is finding one occurrence using binary search and then expanding towards the left and right using loops. Although this approach may appear efficient, it can become often when the array contains many copies of the target. For example, if every element is equal to the target, you may end up scanning the complete array. The third mistake is moving in the wrong direction after finding the target. Remember, to find the first occurrence, search towards the left. To find the last occurrence, search towards the right. The fourth mistake is forgetting to store the current index before continuing the search. If you do not save mid as possible answer, you will lose a valid occurrence. The fifth mistake is using an incorrect loop condition. Using left less than or equal to right ensures that we also examine the final remaining element. So it is not left less than right, but left less than equal to right. Let us quickly recap the complete solution. The array is sorted and we need O log n time, so we use binary search. A normal binary search finds any occurrence of the target. To find the complete range, we perform binary search twice. In the first search, when we find the target, we save the index and continue searching towards the left. In the second search, when we find the target, we save the index and continue searching towards the right. The two returned indices form our final answer. The time complexity is O log n and the space complexity is of O of 1. The most important takeaway from this problem is that binary search is not limited to finding whether an element exists. We can also use binary search to find boundaries such as first valid position, the last valid position, the lower bound or the upper bound. This boundary search pattern appears frequently in coding interviews. Try writing the solution yourself before submitting it on LeetCode. Also test it with an empty array, a missing target, a single element array, and an array containing only duplicate targets. If you found this explanation useful, like the video, subscribe to coinslive, and share it with someone preparing for coding interviews. I will see you in the next problem.